Okay, guys, how are we doing? Ready to get going? Questions about the syllabus? No questions about the syllabus? Everybody understand everything about the syllabus? Understand doing your part? Okay. A couple things I did not mention on Wednesday. Your daily outline is like about the third page, okay? Give you an idea of what we're doing each day. Not everything is here, okay? I can't write every single little detailed topic here. General main topics, we are already behind, okay? Typically, on the far right is your lab schedule, yeah? Check in and lecture downstairs, and then our first lab next week. We'll talk more about that this afternoon after checkout. We'll meet upstairs today after check-in. We'll check in and then we'll go downstairs for a lecture. Can't show a couple other things there. My background is largely in medicinal chemistry, which is drug development, and so I use a lot of drug structures to illustrate principles, topics that we'll be covering. There's a list of some common drugs. You'll see that they're all fairly small organic molecules. Most drugs are. You know, there are some drugs that are more like antibodies or proteins. Many of you know these drugs. Many of you have taken these drugs. Tylenol. Yeah? What is this class about? It's explained several places, different ways. Here's another explanation. You might questions you should be able to answer about ibuprofen. Where are we going? Okay, chemical, what do the dashed lines mean, etc. Hopefully when we get through the course, you'll be able to answer all these type of questions. But then, what can you then go on in other courses and be able to do? And so there's some more advanced questions down below that are beyond the scope of this course, but to sort of give you an idea of where you're heading, and how you're going to be able to use the information. Yes. For those who are looking to fail the course, I include some recommendations on how to do that. Anybody looking to fail the course? Okay. So, a little sarcastic here, but hopefully it's just another way to get you to realize some expectations. Okay? And in the back sheet, you're going to be turning in on Monday here in class. I'd like to get to know a little bit about you, maybe what some of your concerns are, etc. Okay, did anybody not get a handout on Wednesday? We had a green, we had the syllabus, and then we had a white. Functional groups, the other handout. I'll be sending you a good number of handouts over the course of the semester to print. I've already sent you some. I'll send you one more today. It's easier to distribute. Also, I can get it into your hands quicker. And some students have commented in the past, it's just nice to have an electronic copy. So I'm doing more and more of that. Please print. I'll give you plenty of leeway. I'm not going to send you something the night before and say, hey, have this tomorrow. I won't be doing that to you. Okay. We'll say a few more things on Monday to help get us launched, and then we'll be sort of then moving along. Questions today, though? Anything about the course?
For now, are we still meeting this?
Well, today we're meeting upstairs. When we meet downstairs, I'm not sure this room's available. I'll let you know. Please ask again. Remind me like next week. Because next week we probably will meet downstairs at 2:30. But today we're meeting upstairs at 2:30. Okay, let's see where we left off at. I have the outline to help me know where we're at, etc. So you should as well. We were doing some Lewis structures, right? We did one with double bond. Let's go back. What did we have? We ended with CH2O. What did we have here? We had this here, and then we said it was no good. Carbon doesn't have an octet. Okay, we put electrons around oxygen because it's the greediest. We want to make sure it's happy first. But then what did we do? We said we want to take these electrons and move them in and make another bond, yeah? Double bond. This ended up going to be a resonance structure. This is a resonance double-headed arrow. Resonance arrows. And so we moved these in. This is your mechanism arrow. This is you moving electrons. It's got to mean something to you. What does arrow mean? It means this is moving in to make a bond between here. The result of the arrow moving. You can only show the results of the arrow moving. You can't be showing other stuff. Now we have double bond and 2 lone pairs on oxygen. And we got to this. These are resonance structures. We'll define that more and more as we go along. We actually do not cover resonance until test 3, believe it or not. But we're starting right here today. Laying the foundation. We said this is a better structure. Carbon making 4 bonds, no lone pairs. Oxygen 2 bonds, 2 lone pairs. Both have octets. But let's go back over here. Look at this structure. Atypical atoms, bonding arrangements. Probably going to have charge. What's the charge of the oxygen here?
Negative.
How do you know it's negative?
Has an extra electron.
Okay. So how do you determine charge? First off, you have how many is oxygen supposed to have? 6. Periodic table. 6 valence electrons. Okay. Valence electrons. How many does it own here? It owns its lone pairs. So it owns 2, 4, and 6. But of the bond, it's like one of the electrons came from the oxygen, one of the electrons came from the carbon. So oxygen supplied one of the electrons of the bond. So it sort of owned it originally. So it's like 1 and then 6. It's owning 7 in this arrangement we put it in. Well, 7 is 1 more than it's supposed to have. If you have an extra electron, what's your charge? Negative. We want to circle charges and we want to show charges on atoms. I know in Gen Chem you sort of show it up in the corner and say, hey, this thing's charged. In organic, on the atom. What's the charge of the carbon? How many is it supposed to own? 4. How many did it bring to the dance?
3.
How many does it own in this arrangement? It owns 1 of each bond. It only owns 3. There's no lone pair. It's missing 1. If you're missing an electron, what's going to be your charge?
Positive.
Positive. Okay? Now you can look in your textbook and they'll give you some formula. If you just want to plug in numbers and formula, then go for it, whatever works for you. I don't give you formulas because I want to explain it and you to understand what's going on. If you look at a formula, you just plug and chug and it's really no good. Because the understanding is going to let us then apply and discuss other things. And okay. Any charges here? How many does the oxygen own? 2, 4, 5, 6. 1 of each bond. It owns 6. It's supposed to have 6. It's neutral. Same as the carbon, it's neutral. Okay, so that's charges. Formal charges. Okay, these are resonance structures though. Because all we did when we went to here is we only moved pi electrons. That's actually pi electron. That'll come a little bit when we talk about hybridization. Let's see, is this structure reasonable at all? What if I drew you another resonance structure up here? What if we had drawn something like this? If anybody ever can't see, just say, hey, I can't see. I'm assuming you can if you don't say anything. Or let me know after class or whatnot, okay? What about this structure? First off, it's got the right number of valence electrons up there. Any charges here? What's the charge of the oxygen? Positive. And the carbon?
Negative.
Negative. Okay. By the way, every one of these structures is net neutral. That's because CH2O, it must be neutral. Because if it wasn't neutral, I should have given you a charge right there next to the CH2O. Okay, this is best. Which one of these do you like better? Right or left?
Left.
Correct. Why? We've already really said why. Why is this one better?
Oxygen is more electronegative.
Oxygen has the octet. It's more electronegative. It's more demanding, okay? So, while this is best, we can still assess this one maybe compared to something like this. Oxygen has no octet here. It's going to be very mad. It is not going to like this structure. It's not going to be a happy structure. It will be very mad at you. This one's better because of electronegativity and dipole polarity expectations. Okay, so we'll be considering something like more like that along the way. Okay, HCN. We'll be showing overheads throughout. How many valence electrons with HCN? Carbon 4, H1 5, nitrogen 5, 10 valence electrons. Okay, the carbon and nitrogen have to be bonded together because you can't have CHN. H don't make two bonds, right? So CN, where do you want to put the H? Where did I recommend? On the carbon, right? Now, could we have put it on the nitrogen? Yeah, you could. We could maybe get a structure, but I'm recommending carbon first. Okay? That's only 4 valence electrons. We've got 6 more to put up here. Where do you want to put them? Before just throwing up a triple bond, let's do it systematically because as it gets more complex, it's like order up. Okay? You may already see it, but you got to know a process that will help you do a million examples, not just the one you quickly saw. Now, I also will tell you this. Right now, we're doing sort of small molecules. Okay. Once we get larger, I will show you sort of another little approach. Okay, let's fill the valence of nitrogen. It's more electronegative. It's more demanding. Now, nitrogen has an octet. Okay, are we done? Is this a great structure? 10 valence electrons up there. Carbons don't have an octet. What's the charge of the carbon? Yeah, 2 plus. Charge of the nitrogen. 2 negative. Negative 2. Yeah? By the way, we'll rarely ever see negative 2, positive 2 in this course. Usually beyond 1 is reserved for metals. Like iron plus 3. Not inorganic. So this is pretty bad. Okay? What do we need to do? Start putting more lone pairs around carbon? No, we don't have any more electrons to put up here. What do you want to do? We got to ask nitrogen to start sharing, okay? We know you'd rather pool. Okay, oxygen, we know you'd rather keep those yourself maybe, but okay, but maybe you'd like to share some. And sharing some makes the whole molecule happier. So how can we show this on the board? These two electrons move in here. Let's do it one at a time. What does that give? What does that arrow mean? Now we have two bonds between nitrogen and two lone pairs left. One moved in. What's charged here? That's positive and that's negative. Is that structure good?
No.
Better. Better, yes. Carbon still doesn't have an octet. Well, let's ask nitrogen to share again, and we can get another resonance structure. Resonance structure is because all we're doing is moving pi electrons. We're not moving any atoms or disconnecting anything. And so now we have what? What does that arrow mean? Another bond, and it's actually what we're going to call it a pi bond. And we get to this. How do you like that one? Carbon, 4 bonds, no lone pair. Nitrogen, 3 bonds, 1 lone pair. It's a triple bond between the carbon and the nitrogen. By the way, what's this functional group called when you have a C triple bond in? Cyano or nitrile. Okay. It's really just an H. It's hydrogen cyanide. You got to be careful about the I. It sounds like an anion. There you go. There's a good structure. Triple bond through sharing. DUS. We need to look at DUS. This structure has 1 DUS, degree of unsaturation. By the way, I should have said this. You can look at that formula right there, and you can tell it's got to have a triple bond from formula. That's understanding DUS. DUS is very helpful. CH2O, you can look at that formula and tell that it's going to have a pi bond or a ring, but you can tell something from formula. And we have 1 pi bond. We'll talk about that. Saturated. Let's see if we can move in to talk about that. And functional groups. What functional group is this? Well, let's pretend like this was maybe something else. Anybody know a functional group? Yeah? Anything there?
Carbonyl.
It's a carbonyl. Carbonyl is not an exact functional group. It's a part of functional group. Somebody said it's like an aldehyde. But it's almost like a double aldehyde because you got 2 H's. Usually aldehydes have another carbon here and only 1 H. That's formaldehyde. Formaldehyde, 1 carbon aldehyde type. So functional groups and DUS. Okay, we have that handout. I sent you the DQ. DQ, is that right? That's something to get started on. I explained that in the email. Questions that we could maybe look at. Well, everybody has looked at them ahead of time, particularly those. Where all the other questions in the workbook, you might have looked at the same one. Functional groups. Many of my handouts will begin with a warm-up. These are questions that hopefully you'll be able to answer after we get through with the material. Questions that help sort of stimulate some interest. Let you see how well you know the topic before you even get into it. For example, if you read some of the questions and you have no idea how to answer them, well, that tells you need to spend some time on this topic, right? So those are the kind of things the warm-up is meant to get at. Was another source of questions. Of course, you have questions in the workbook. At least questions from me. And then your textbook, of course, has many, many questions to be working for practice. DUS. I feel like I want to look at DUS first. Okay, DUS is very important, very helpful for you. You can determine DUS two ways, either from structure or from formula. You need to be able to do them both. This molecule has 1 degree of unsaturation. Okay, 1 DUS. Some textbooks maybe call it an index of hydrogen deficiency or something, but they'll probably still have DUS in the text. Okay, from structure. 1 double bond is 1 DUS. Okay, 1 double bond, 1 DUS. 1 triple bond is 2 DUS. Okay, like ACN. Triple bond. That's really because each pi bond is a DUS. There's 1 pi bond here. There's 2 pi bonds there. Once we do hybridization, then you should know that. Okay. Also, a ring is a DUS. You have a ring, that's going to count. Now, DUS is unsaturated. Degrees of unsaturation. Well, what does it mean to be saturated? Saturated refers to hydrogens and having the maximum number. Okay? Cn. If you just have a molecule with Cn, okay, the maximum number of hydrogens is 5. How do we know that? We'll get it there. Okay? If you have, thus, if you have a, well, we're doing structure first. I kind of blend the discussion together. Thus, if you have something like CH3N, if this was a formula, and if you know it's saturated with 5, is this saturated? No, it doesn't have 5, it's got less. So we call this unsaturated. We're referring to hydrogens. It's got less than max. All right? Now, for example, CH3NH2 could be this structure here. It'd be difficult to have, I reckon you could have other structures, other isomers. Okay? How many pi bonds do you see, or double bonds, triple bonds? None. How many rings do you see? None. It has no DUS, if you base it on structure. Here, though, we see a double bond. There's 1 pi bond, there's 1 DUS. Okay. These are called hydrocarbons because they're just hydrogen and carbon. The maximum number of H's for a hydrocarbon is pretty simple. It's the simplest. It's probably written there. I'm going to rewrite it so I don't have to hunt for it. 2N plus 2 equals saturated. Okay? For hydrocarbon, where N is the number of carbons. Okay? Look at this structure, 2 carbons. So if N is 2, what does the formula equal? 6. Times 2 is 4, plus 2 is 6. So 2 carbons would need 6 hydrogens. Okay? You see the 2 carbons with the 6 hydrogens? It's saturated. Now this one over here is C2. We know for 2 carbons saturated is 6. Do you see 6 H's here? No, it's only 4. It's unsaturated. But you can also see that because we know that 1 pi bond is unsaturated. Now typically unsaturation comes in groups of 2. You're never just missing 1 H. You're either missing 2 H's or 4 H's or 6 H's, or maybe you're missing 12 H's, multiples of 2.
So if you get an odd number, that's a good indicator that you've done it wrong.
Odd number of DUS? No. Odd number of missing hydrogens. But that's only if it's hydrocarbon. If it's got a nitrogen involved, it's going to be, well, still multiples of 2, but it's an odd number. There's lots to it. Let's go through and then you can see what you need to be thinking about. Okay. C3. Don't look at how many H's there. What's max for C3? 8. 2 times 3 plus 2? 8. 8 would be saturated. So if you saw C3H8, you know that's a saturated hydrocarbon. That means if you put together a structure, you better not have any pi bonds or rings because you would have some unsaturation. The formula indicates no pi bonds or rings. Here you go, totally saturated hydrocarbon, no pi bonds or rings. Here we go, we have a ring. See, to make a ring, you bond these two carbons together. But to bond the two carbons together, you have to take an H off of each carbon. So you have to remove two H's to make a ring. So that's why it does not have 8, it only has 6. Okay, you can look up there, some things I skip over, that's because you can just read it on your own, etc. Do a couple more examples. Okay, from formula. Well, I've already been talking about formula there. We worked it in, What about when heteroatoms are present? Non-carbons, like the nitrogen. The 2n plus 2 is just for hydrocarbons. Okay? What if you have a nitrogen? What was the formula up there? It was CH5N. What was that sort of structure up there? CH3NH2. It's shown more informative, but it's H5 total, right? So if you saw this, how many DUS? 2n plus 2, 1 carbon. 1 carbon is 2n plus 2 is 4. It's got 5. It's got more than this. It's more than saturated. That don't make sense. It's because what does the nitrogen do? How does it account? Well, you don't plug it in the 2n plus 2. It's not N. N is carbons. How does the nitrogen count? Okay. It says here, when you're looking at formula, a halogen counts as a hydrogen. A nitrogen subtracts an H. So if the nitrogen subtracts an H, the fact that we have a nitrogen, we can get rid of it and subtract an H. This turns into CH4 because nitrogen subtracts an H. Now, 2n plus 2 is 4. There you go. Saturated. You have to know how the heteroatoms, how you need to adjust for the heteroatoms. Oxygen you just ignore. For example, if I just showed you CH4O, just ignore it and assess it like a hydrocarbon. CH4O, is that, how many DUS? Well, we ignore O, right? 1 carbon, 2n plus 2 is 4. How many H's we got? 4. It's saturated. You just ignore the O, so that's the easy one. Question?
Do you subtract 1 hydrogen per nitrogen?
Yes. If you had 3 halogens, you would have, no.
Okay.
Because if we had C6, H, 2, Cl, and I could make Cl, bromine, fluorine, all halogens, but I'll just make them all together. Cl4, okay, how many DUS? What does halogen count as? How do you deal with halogen? So how many hydrogens is here if we adjust?
6.
Yeah, we can turn that into this and now do our 2n plus 2. Because halogen counts as an H. So there's really 6 H's here in terms of what we're doing. So how many DUS?
1.
4. 4 DUS. Right? 2n plus 2 is what? 12 plus 2 is 14.
Minus 6
This is what we haven't done yet. Saturated would be what? Saturated for 6 carbons is 14. How many are we missing?
6.
8. Missing 8. So how many DUS?
4.
It's actually 4. Okay, I haven't said it yet. Every 2 H's you're missing is a DUS. Remember, multiples of 2. This is missing 2 H's. That's 1 DUS. This is missing 8 hydrogens from max. It's 4 DUS. So this compound could have how many pi bonds? 4. It can't have 5. If you drew a structure with 5 pi bonds, something would be very wrong. It could have 4 rings, but it can't have 5 rings. It could have 2 rings and 2 pi bonds, but it can't have, okay? There's an example here with Prozac. This formula can be turned into this. If you adjust, okay? Ignore oxygen. F's can be, fluorines can be counted as hydrogen, so that changes this to 21. And what does nitrogen do?
Subtract 1.
So we subtract 1, we go to 20. So this is essentially this. 17 times 2 is 34, plus 2 is 36. 36 is max. How many is it missing?
16.
16 divided by 2,
8.
8 DUS. Okay? So we know a little bit about that structure of Prozac. If we want to see a structure of Prozac, look on the drug sheet in the syllabus. Bottom left. Here we go. 8. Do you see 8 DUS? How many rings?
2.
2 rings. How many pi bonds? Which is the second bond of the double bond?
6.
6. 6 and 2 is 8. You see the 8 DUS by looking at structure? So we did structure and we did formula. Determine it both ways. Everybody see the 8 DUS? Formula can be very informative. Anything we do, you need to sort of digest it a little bit, okay? See what type of questions we have next time. I can say that for any topic we cover. Our class time is limited. 90% of your work is outside of class. 95%. Okay, functional groups. Functional groups are particular arrangements of atoms. We arranged this way and we ended up with an aldehyde. But it's terminology. It's the architecture of organic molecules. Okay, this came out of a book called by Smith. Every textbook presents them a wee bit differently, but these are the ones that you're accountable for. Okay, the top table is just hydrocarbons, only hydrogen and carbon. Your alkanes, these are just saturated hydrocarbons. Saturated, you see? Now, this is a sort of a condensed formula. They're not saying C2H6 because that's the most generic you could show. They're giving you a little bit of structural information, like I said. So it's 2 methyls bonded together, all right? And you'll see that. Your alkenes, the ene ending is where you have the double bond, carbon-carbon double bond, called an alkene. Now here you have to have at least 2 carbons. And so that's the simplest alkene you can have. And you see 1 DUS there. Of course, the alkene is a DUS. Your alkyne, ine ending is your carbon-carbon triple bond. That's the simplest alkyne. That's actually acetylene. Acetylene gas. Plain hydrocarbons. You can also have aromatic hydrocarbons. And you can have a few other miscellaneous types, but this one's pointed out here. Your most common aromatic ring is your benzene ring. Okay, 6 carbon ring, 3 pi bonds formerly, and you see it's got some unsaturation. Now, it says functional group over here. We'll have to talk about that. To me, the functional group is really on the left. I don't really like this wording here. The chemistry of benzene is covered mostly in organic 2, but you do need to be able to recognize and understand a little bit here. You can call the benzene ring a phenyl group. So those are some plain hydrocarbons. What about compounds that contain more than just C and H? Okay, many of them down here. If you slip in a halogen, these are called alkyl halides. Okay. You can also have aryl halides if the halogen's on an aromatic ring. Alkyl coming from like alkane. The white L meaning it's sort of a substituent or a fragment. So an alkane halide. Alkyl halide. This is an aromatic halide. We're called aryl halide. Examples there. Okay, let's move through these. Alcohol. First off, what's an R group? You're not going to find R on the periodic table. R is a designation with just a plain carbon group. It can be 1 carbon, it can be 17 carbons. Okay, lots of variety it can be. So this is a plain carbon group with a halogen bonded to it. We have an R group, plain carbon group with an OH stuck there. It'll be on the end because H only makes, okay. This is an alcohol. The example would be like a methyl alcohol or methanol. Again, these are your functional groups. I don't like this name. This is more of an alternative or a secondary type name. For example, we call this an alcohol, but particularly the OH is called your hydroxy group. A lot of times we'll put an L on the end of that, hydroxyl. Okay, an ether is where you have oxygen with R groups on both sides. Not just one side, both sides. Like this. Dimethyl ether. The R groups do not have to be the same. Your OR group is called an alkoxy. Why is that hydroxy? Because it's hydrogen oxy. Hydroxy. Well, this is an alkyl oxy. How do we shorten alkyl oxy? Alkoxy. Makes sense, right? Okay, nitrogen. An R group bonded to a nitrogen is an amine. Now with amines, you can have 1 R group on the nitrogen, you can have 2, or you can have 3. They're all amines. With oxygen, if you put an additional R group on, it becomes a different name. With amines, that's not the case. They all are amines. And since nitrogen makes 3 bonds, you could have up to 3. Now, you can actually also have 4. But with 4, it's going to be charged, and that's sort of unique. We will see 4. We also have this terminology for the substitution. With 1 R group, it's called primary. 2 R groups is called secondary. 3 R groups is called tertiary. And 4 R groups is called quaternary, often shortened to quat. Okay.
Will we be specifying that if we were to have to name a functional group? Would we have to specify that as part of the
Potentially,
group?
yeah. I mean, you need to know that, not just here, but we'll see it in other places. So, sulfur, both sulfur. These are analogous to the oxygen because sulfur is under oxygen. ROH alcohol, RSH is called a thiol. Also called a mercaptan. Thiol is the most common. Thiol is used in biochemistry. You sometimes hear mercaptan And the SH group is called a mercaptan group. You don't really hear that too much as a group, but you do hear mercaptan sometimes. Thiol is most important. R group on both sides is a sulfide. Gotta be careful. The "ide" ending in Gen Chem typically means anide. Not always the case. So you do have to be careful. It's not an anide. These are not that important. Don't hear those that much. Okay, on this page we have functional groups that contain the carbonyl. C double bond O is called carbonyl, but that's not a precise functional group. Many contain a carbonyl. Aldehyde. This is carbonyl with H on one side, carbon group on the other. You see, that's why over here, when I had H on one side, I'm like, okay, let's pretend there's a carbon group here. Now it's really an aldehyde. With two H's, it's kind of still an aldehyde. It's really nothing else. Example would be like methyl. Again, the liberty here, those H's are not bonding to that carbon. We could have drawn it like that. But the H is only sort of the outside of the carbon where they really are. The reason people draw it on the inside is because when you're using a typing program, it's just as easier to type, and so you see that type of thing. What I'm trying to get at with this is when you look at a structure, you got to understand these things, because you know bonding. Okay, R groups on both sides of the carbonyl ketone. Most of these examples are just using one carbon. Methyl, it could be 5, 6 carbons. And they don't ever have to be the same. They could be different. See, this is what I don't like. Functional group, carbonyl. That ain't a functional group. That's a component of a functional group. Carboxylic acid, like acetic acid. R group on one side, OH on the other. It's not an alcohol, because if the OH is bonded to a carbonyl, it's a okay, so these take precedence. Carboxylic acid, that's acetic acid, carboxy group or carboxyl group. Ester, R group on one side, OR on the other. Put an R group here, now an ester. Amide. Amide is R group on one side, nitrogen on the other. And with your nitrogen compounds, you can then start putting R groups on the nitrogen. And when you do, the name is still amide, just like amines. And thus you can have primary, secondary, tertiary amides. This refers to the number of carbons attached to the nitrogen. If it's NH2, there's only one carbon attached to the nitrogen, primary. Okay? If that was a methyl and that was a methyl, then nitrogen would have 3. It would be tertiary. So it's the degree of substitution of carbons on the nitrogen. This is sort of a unique one. We'll see it more in organic too. R group on one side, chlorine on the other. That's an acid chloride because it comes from the acid. You make them from acids. Or an acyl. However you want to write it. Acyl chloride, we'll see that. And with those types of things, your other halogens are just not commonly seen in that type of arrangement. The chlorine is the most common one. We're back over here with our like alkyl halides. You can have bromine, iodine, fluorine, any halogen back over here. Okay, down at the bottom, there's 2 more that I want to add to this list. These are often included. This particular table did not include them. Very important. C triple bond N, nitrile. I've already mentioned this, yeah? What's another term for that? The group can be called a cyano group. Yeah? And then this one. Sulfur, 2 oxygens, nitrogen. Okay? And then you can have substitution on the nitrogen. It can be primary, secondary, and tertiary group. This is called a sulfonamide. If you just look at the ending, amide or amide. We've seen amide before, right? What was an amide? Nitrogen bonded to a C double bond O. That's a plain amide. This is also called a carboxamide. It's a long name. Carboxamide because it has the carbonyl amide. Carbonyl amide. Sulfonamide is another type of amide, sort of analogous, yeah? Where the C double bond O is replaced with an S double bond O, but double. 2 double bond O. It's another type of amide. But it's called a sulfonamide. And you never remove that part. You would never just call this an amide. Because just calling something an amide refers to the carboxamide. Okay. You have a little example here of identifying functional groups. We're about out of time. See what is there. We'll pick up next time. Let me say a few things. We'll be moving to hybridization. We've got the outline here where we're going to be heading. You're looking ahead. Also, you have problems to be working.
Which one?
Workbook. Identify functional groups. Identify numbers of DUS. Draw Lewis structures. Please get started working on problems and writing down your questions. See some of you this afternoon. Have a good weekend, guys. If someone would mind closing the camera each day.